in Europe, South America, and the Caribbean, and currently is a professor in the School of Earth and Environment at UC and the director of the GRI. Our second speaker, Professor Moller, is a radar system engineer who previously worked at NASA's Jet Propulsion Laboratory, JPL, and is the founder and principal engineer of Prestor Lab Limited. She has led numerous projects involving ground-based airborne and spaceborne remote sensing systems, and she has won multiple JPL and NASA awards, including being a co-recipient of the NASA Space Act Award for a planetary landing radar design. Currently, Delwyn is a professor in the Department of Electrical Engineering at the University of Auckland. So I'm very pleased to have you here today, and please welcome them both.
Thanks, Maria. Didn't know about that award before you started to do your profile, Delwyn. Also a New Zealander of the Year from which year?
No, not New Zealander of the Year. It was Kia Award winner.
Kia Award winner. Yeah. Almost the same. Future New Zealander of the Year. So you can see here a live tracker of where Rongowai is currently, and we'll come back to explaining what all those pink squirrels on the map mean as we go through the talk today. Let's just swap over to that. All right, so we're going to do a bit of a team tag here to take you through this Rongowai and what it all is. I'll just try to hide some things. So great to see so many people here and online as well. People joining us from outside of the country as well, which is really awesome. There's lots of interest in the mission. Not only within New Zealand, but internationally too. So thank you for joining us. This is a GRI seminar in conjunction with the IEEE GNSS Geoscience Remote Sensing chapter for New Zealand, which is brand new. Had a meeting today. So that's been established in the last few months. Delwyn's the chair if you would like to ask her about that later. What we're talking about really is looking for using signals of opportunity. So these are signals out there that are being used for other purposes, in our case, for global navigation satellite systems. They're these are satellites that are broadcasting signals for a particular purpose, and we're repurposing them for other things. So what you can see there is a GPS satellite, and you can see lots of GPS satellites in orbit. All of them are broadcasting these signals. And so what Rongowai is doing, and what other missions that are using signals of opportunity are doing, is taking the signals that are reflected from the ground and then recording what's received at the sensor, and then inferring things about the surface of the ground from those signals. So those signals get changed by the characteristics of the ground, and that's what we're particularly interested in. In particular, things like moisture on the ground, surface water. So we'll come back to all of that. So what Rongowai is doing is providing a first demonstration, if you like, of polyometric GNSS, GNSSR, that's just Global Navigation Satellite System Reflectometry. And that is going to provide a long time record of the signals that are coming from a really very diverse terrain across the country. So New Zealand has such high diversity in its terrain and the land covers and so on, both dynamic, both in terms of space and in terms of time. And that makes it a really excellent test bed for the technology to be deployed elsewhere. So it's of course it's not starting from scratch. There's been things like Cygnus or the Cyclone GNSS observatory running for several years. And so what you can see here is that you've got a GPS satellite there broadcasting its signals as it usually does. And what Cygnus observatories are doing, there's 8 of them, is recording what's being reflected from the ground from those signals. So it's just simply monitoring what's being reflected. And then as you'll see in a second, those signals are then processed into other things of interest. And so you can see the specular point there, and the glistening zone, that's where the signal is being reflected from. And you'll see the specular point in the Rongowai data as we come to that as well. So this is really cool stuff. And there's really some good advantages to using these signals of opportunity in terms of cost and availability. And the reason it's called Cygnus is because it's the CY part is the cyclone part. So the original design of the system was to monitor cyclones. That does mean that the orbit of it is constrained largely to the tropics and a little bit outside. And so in New Zealand, we only have Cygnus observations in Auckland and North. And but you can see some of the products that are being drawn out from there. Of course, monitoring cyclones was its original purpose, and you can see how cyclones look with Cygnus data. But it turns out that those signals also get attenuated and changed to quite a strong degree by things on the ground like surface moisture or soil moisture, and also surface water. So two examples here is a global, or where we have Cygnus observations, monthly mean soil moisture for April 2018. And we also have the aftermath of Hurricane Harvey there as it made landfall in August 2018. And so we can see, we can use these observations to map where surface water is, but also infer what soil moisture is in locations as well. There's also future missions in this area. GNSS is from the European Space Agency, and this is targeting in particular the cryosphere and hydrology, and it's using polarimetry as well, as is Rongowai. So you can see that Rongowai is, the data from Rongowai is helping to inform the design of algorithms and things for GNSS, but it works in a similar principle to Cygnus. Planned for launch October next year. So we've been talking about spaceborne platforms, and there's always a compromise in remote sensing between the platforms that you're flying from. So spaceborne is great. You see very wide coverage, perhaps global, but you don't see so much details necessarily. With aircraft and drones, you see lots and lots of details because you're flying much lower, but you can't get widespread data. So particularly with drones, you're seeing very close to the ground, so you get lots and lots of detail in a very small area. With an aircraft, you expand up and you can see more information, but the level of coverage that you might be able to get is constrained by where you can operate the aircraft and costs and things like that. So that's informed the design or the idea behind Rongowai. So I'll bring Delwyn up because Rongowai idea really is your baby. And the example here is radar, which Delwyn's a radar engineer. She can explain what all this means. But
so hi everyone. Yeah, so along that, I'm a big proponent of really custom designing what you're trying to do with your Earth observations, and it's all about the marriage of the sensor and the platform. And so different scales are appropriate for different types of observations. It's all about your spatiotemporal sampling and what you're trying to get after. And this example here is for an imaging radar, which is, synthetic aperture radar is kind of, they're often incredibly complex and data hungry as well. And so these are the kinds of systems I've traditionally worked on. And, we have and usually I've worked on millimeter wave interferometric systems. So again, quite complex, a lot that goes into it, huge amounts of data, all of this kind of stuff. And in proving out this capability, flight types of observations and being able to put it on the plane and test it is absolutely crucial, not only for the science, but also when we do launch something, we really want to know that it works and have our algorithms sorted and all of that kind of stuff and prove out the technology. And so, but it's hard to do because flight hours and access to aircraft is usually really limited. So if you're lucky, you get a campaign. And we have a couple of example systems here, one on the NASA G3 and that pod under there. And this is one that is close to Tamla's heart, who's here. This was up in the Yukon, and we're flying what's called air SWAT. and a precursor to a mission that's now launched and is producing amazing data called SWOT. And so that's near and dear to my heart. But, you know, again, what you can do with aircraft is often limited to those science campaigns or those pre-mission campaigns, and the time that you manage to get access to that aircraft and the amount of money that you have to get to do it. It's usually just really difficult. So, you know, one of the questions is, what if we could take advantage from a scientific perspective of the aircraft that are already flying all the time, the commercial passenger lines? It'll need to be compact, need to be passive. We're not going to have something that's actively transmitting on a commercial. It's just not going to get off the ground. Need to be maintenance free. So you can't have something with all of these masses of data that we get from these imaging radars. It's just not going to happen. You know, how do you offload it? And also you want it to be impactful and compelling. I mean, because then we're turning from a campaign into a mission, right? So let's do something that's meaningful. So for that, GNSSR is ideal. It's independent of cloud cover, which is a big issue in New Zealand. We don't see things a lot because we have a lot of cloud. Aviation GNSS antennas are already available and they're flying routinely all over the world because the aircraft use them anyway. It's completely passive. It only receives signals that the aircraft is already using anyway. Compact and standalone. And we're fortunate that we have missions like Cygnus already there. So there's already compelling leading edge science with private and public sector impact. So we can already do something impactful whilst doing something that's relevant and enabling for, you know, what is a growing field and next generation EO space missions. So this idea was floated a few years ago now. I was fortunate enough to talk to the engineering staff at Air New Zealand and then talk to their chief engineer and said, hey, can I put something on one of your planes? And he's like what? And which I nearly fell off my chair when he said that. But then we floated the idea of GNSSR. I talked with Prof, who's the Cygnus PI, and they have a next gen GNSSR unit that they have developed under NASA funding, and the agreements took place. Air New Zealand agreed that they would certify and fly it, and NASA agreed to fund the development for it to be transitioned to autonomous operation, and MB also for the New Zealand Space Agency. They said this is a win-win for everybody. So you see lots of happy people shaking hands. So in this unique international collaboration, where we are now flying a GNSSR unit, it's the next generation, so it's got more technological capabilities than Cygnus on the Air New Zealand aircraft. So if we do a little comparison down here, Cygnus is compatible just with GPS. We're compatible with GPS and Galileo, L1 and L5, although presently we're only doing the L1 level. The big benefits that we get is instead of 4 channels, there's 20 channels on the NGRX, which is what we're flying. That means we can get 10 satellites simultaneously with 2 polarizations. So we've got copole and crosspole. And so that's a unique new measurement capability that we're doing also. So we get more coverage and we get polarimetry, which is completely new. And so this is kind of a graphic of what we're doing. It's opportunistic. This is, to my knowledge, for something like this, a world first between NASA and a commercial passenger airline. The near-term science benefits, and we'll be showing you some kind of initial science results Matt will be showing, is for wetland and soil moisture monitoring, coastal dynamics, ecosystem health. So some of these things like ecosystem health are kind of longer term to fall out of this. Also long-term monitoring of local and regional climate change impacts. And one thing that's growing but has been just so much fun is the engagement that we're having with the international community, working with our NASA colleagues, and that as the data is starting to come out, that is really ramping up. I'm hoping this sets the stage for more of these kind of partnerships and activities, really taking advantage of these platforms. I thought I should introduce the Rongowai name and the Rongowai logo. Rongowai is the name that we were gifted. And in Te Reo Māori, it means, Rongo means to sense, and Wai, of course, is water. So to sense water, and it means it in every kind of facet of the way to sense, to touch, see, feel is Rongo. The logo design was done by a local student artist, and it's a manaya. And in this instance, the manaya is a kaitiaki, or a guardian of all bodies of water. So there's quite a lot of depth to this logo, actually. The differing hues of blue account for the differing tones of Wai across the world. But it's also a lens or a whātu, revealing a state of Māori ora, or thriving life force. So the land's thriving due to the Wai that feeds it and all its forms and sources, rivers, lakes, the ocean. And the curved head of the manaya is actually a river that turns inward to replenish the land, or the whenua. So I think this is a really lovely, meaningful name for Rongowai moving forward. And up in the right is a picture of the actual unit that's installed on the Air New Zealand Q300. It's underneath the floorboards. You'd never know it was there. It's just like a dumb passenger that sits there with the logos of all the major participants. I'll go over this fairly briefly. The main point of this view graph really is with our NASA colleagues from University of Michigan, Ohio State, etc. They went to a lot of effort to characterize this very well before we put it onto the aircraft. So unlike the campaigns that I've done in prior, this one, we really are treating it kind of like a mission. It goes in the floorboards. It was installed as part of a major maintenance activity. And to pull a commercial plane out of service and do this, it's not very practical. So basically, when we put it on there, we're banking on not being able to see it again. It's gone. It's like launching something. So we went through a lot of effort, or they went through a lot of effort to really characterize the antenna pattern and the cables and all of the losses, so that we're basically putting something on that's extremely well characterized, so that we don't have to pull it off and go, what's going on here? In terms of operations, we have a payload operations center. It enables us to do flight software updates, etc. Also flight tracking capability. You saw that at the beginning. We know where we are at any given time. We can track the aircraft and kind of predict where we're going to get, what kind of coverage we're getting. But also just the engineering health. Is everything within limits? Are the temperatures within limits? Is there anything going over current? Is there anything we need to worry about? So we just have that routine, and we get automated unpacking of the science and engineering data, but also automated, you can get a text message if something does go out of range, to go pay attention, because frankly, nothing ever happens. So it gets a little boring because it's always in range, which is great. And we installed on, so we have had a maintenance period where they pulled this off into, I think it was actually in Christchurch, yeah. So it was installed in Christchurch in their facility here. And that was August, September at the Christchurch. They basically pulled all of the interior out of the aircraft. Everything's out, it's totally gutted. They put the cables in and put the seat back in, and all of they were doing other maintenance just as up, but we went in at that time. And the first flight occurred 13th of September, which was a Christchurch to Nelson flight. And since then, we've been everywhere. But I really liked these headlines that came up. So I thought it was really cute. Air New Zealand says we have liftoff, and NASA says they're racking up frequent flyer miles, which I thought was kind of a neat shout out. And so this was a clip.
Ship shape on a flight so groundbreaking, the captain's practicing a new onboard welcome.
Riddle, did you know that when you boarded the service this morning that your journey would be part of a NASA climate science mission?
So I thought that was really awesome. Air New Zealand has been amazing through, and such good, so supportive and proactive on this. So for those of you who in the geophysics area and like working with data, we have what we call DDM data, or digital delay map data. That's really the guts of your science data, and we'll talk about what that looks like, and we'll give some examples in a moment. But the NGRX, the system, the Rongowai system, supports 20 DDM, so 10 right-hand circularly polarized and 10 left-hand circularly polarized channels per at any given time. And basically from that we get derived products that we'll be showing you in terms of, we can tell if it's land, if it's water, and then if it is land, the relative dryness of that land. And then hopefully with polarimetry, we'll be starting to tell you something about we'll be able to derive stuff about the vegetation cover, etc. And also in the ocean areas, you know, how inundation patterns are changing in coastlines, but also winds, as they do for cygnus in the regions that we're covering. So the science telemetry is what most of you are interested in. There's also NAV data, raw AF data, which is really a lot for fine tuning or looking into the guts of the system. Most people will never want to look at that. And then your basic engineering data. So, you know, making sure that everything's healthy and flowing as it should. And just to give a better kind of a high level overview. So the plane lands. So while it's flying, it's collecting the data. When it doesn't transmit anything until it lands. So, you know, when you land on a plane, they say it's now safe to turn on your transmitting functions. We turn on our transmitting functions and we phone home. So the data gets offloaded off the plane, just goes over a regular cell service and gets received. And then that's called our L0. That's unpacked. This is all autonomous. And then some of the data gets streamed to an engineering check. You know, those boring looking plots are showing you just, you know, was everything good in the last flight? Was the system happy? You have a person that can look at that, evaluate that. If there's any collection plans or flight software uploads, we can do that when the plane is on the ground and power to it. That's very infrequent. And then there's what we call the L1 processing. That's the stuff that really has the first level of what it takes that any of you can run off and turn that into something that's geophysically sensible. So you can take the information within that and turn it into soil moisture maps, turn it into standing water maps, turn it into any number of derived applications and products. And Matt's going to talk about that in a minute. So the things that are coded and that are colored in the orange yellow, those will be made open and available to everybody. So the international science community, international whomever. So that stuff will, the other stuff you probably don't want to look at, no one would care, and you'd have to know about the system intrinsically, and you know, but the L1 will be available and also turned into a number of other products. But these other ones, they're really collaborative contributions from the community. So there might end up being, for example, several different types of soil moisture products, gridded and otherwise. And as long as, and we hope that those contributions end up being part of, again, the international research community and openness in terms of the algorithms that go into this and the basis of deriving those. But along those lines, I think this is maybe a good place to turn it back over to, is it over to you next? Oh no, one more. Just a summary of where we're at to date, and this is up to March, so we've already got another month on top of this. So if you look on the left, this was the predicted coverage for 1 year of Q300 domestic flights on a single aircraft. And this is the actual coverage over 4 months. And you can see we're pretty much following, we're right on track for that. And obviously we get good dense coverage over the routes that the Q300 will fly. One thing that's been really fun as this mission has been taking place, is seeing how because we're just a passenger, we don't control where it flies. It tends to fly the way that they schedule it in a kind of a hub and spoke pattern. So we'll be in Auckland, we'll ping pong back and forth out of Auckland a bunch, and then we'll end up in Wellington, we'll ping pong out up and back out of Wellington a bunch. Christchurch do the same thing. And so you get kind of this fast time sampling, and then you kind of come back around to where you were before. So you also get this longer time sampling. So it actually, if I could have designed it, I probably would have done that, but I didn't. That's how they do it, which is just awesome. This is another thing that just kind of like, you know intellectually, but once it's happening, you just go, wow, this is cool. We had 969 flights from October to 5th of March. Those are science quality flights where we're going to get geophysical information out of it. We got struck by lightning in our first month, which was a bit of an nail biter, but everything's fine. We have a lightning arrestor and it worked. And Matt's going to show you some stuff here of one thing that we managed to capture was flooding events in Northland, because we happen to be flying up and over Northland, back and forth, while there's active flooding going on. And so that's going to be really fun data to dig into. We've only just scratched the surface on that. So there may be some relevance to this if we're in the right place at the wrong time, if you like. There is actually kind of a short time frame type of capability that this may be relevant information. And we have a 7-year mission life. So that's longer than most spacecraft mission designs. So we've got 7 years of this is going to be happening. Okay, now it's Matt.
Okay, so to give a bit of a better idea about what's happening in each flight, we put together this animation. And what you can see here is the aircraft flying along, and once it reaches a certain altitude, the sensor comes on and starts recording data. And it's recording the reflections of those signals, and those are represented by the specular points in yellow there. So it's tracking each of these different 10 satellites and recording the location of those specular points, and those then form tracks along the ground. You can see those forming in the yellow there. And the lines from the yellow specular points there go back to the aircraft. That's where it's being reflected to, and where it's coming from are the GPS way up in 22,000 odd kilometers away. And so as we zoom out here, you'll see that. So if you think about what's going on here, it's actually it's pretty amazing. Actually, all of this coming together. Keep zooming out. Eventually get there. So so these are actual flight data that's been recorded for flight Christchurch and Nelson on 5th of November. And you can see the orbit tracks, the partial orbit tracks during our flight there. So we're tracking these GPS satellites, which are broadcasting, as they always do, their signal being used for other purposes like navigation. And we're recording where those signals get reflected from and getting information about that location on the ground, that specular point location. And so this is, as Delwyn was just showing, this is 7 or 8 flights per day on average, all over the country. I don't know about you, but I can watch this all day. But so, and at the moment we're developing the algorithms and things to start processing these data into inferring what's on the ground. I'll show you some of that in a second, where we've got to. Oh. So the 2 initial key data targets, although they are only initial, are soil moisture and surface water. So these are things that we're focusing on initially. But as Delwyn was saying, the other application areas include things like coastal ocean and vegetation. We can start looking at that as we go through that 7-year program. There's so much you can do with these data. And I'd say as well, re-emphasizing they'll all be available to the community. So it's not just us that's going to be processing these data, that everyone is welcome to. So I'll show you some of where we've got to so far with those 2 things. And because of it taking quite a while to put together a sensor and get that onto the aircraft, that's a huge amount of work. During the funded science program that we've had over the last couple of years, one of the things we've focused on is developing the methodologies that we can then apply to the Rongowai data to get us ready to go. And because Rongowai builds on the Cygnus mission, and because we have NASA colleagues involved in Rongowai as a result of that, we can share expertise and share ideas and share algorithms and so on. So what made perfect sense for us to focus on processing of Cygnus data to be able to get up to speed on what Rongowai is going to look like and what some of the nuances are in those kinds of data and so on. So what we've done initially is focus on building a machine learning framework for processing Cygnus data for soil moisture that can then be transferred to Rongowai. So we're going to apply the same methodologies that we've developed for Cygnus onto the Rongowai. And here's how it looks, the framework. We pull in, and bear in mind, we're moving from New Zealand scale to global scale here, so there's huge amounts of data involved. So we pull in all the Cygnus data, literally all of it, and a whole bunch of soil moisture in situ locations from an international soil monitoring network, and a whole load of ancillary data, which we use as covariates in the machine learning. So those are providing information about what's on the ground already. Things like vegetation. I'll show you a few examples at the moment. We pull those into a combined database. So we have at the locations on the ground, we have the Cygnus observation, we have a soil moisture observation from a gauge, and we have a whole bunch of ancillary data as well into a combined database. And then that gets used in machine learning, training and testing to give us a soil moisture estimate. So to be able to do that, of course, what we need is to take that specular point location and co-locate it with a soil gauge, which has a location as well. So we've got 2 points, if you like. Not quite a point for the Cygnus, because we have the Fresnel zone of where the area is being reflected from. So we take a buffer around the specular point location for Cygnus, initially of 2 kilometers, to co-locate a soil gauge with the specular point for Cygnus, and then use that to identify the gauges that are co-located and use the area around the gauge to put in the other ancillary data too. Most of those gauges you can see are in the United States. There are several around the world as well, some in Europe and Africa as well. So what we're doing is, like, using these data as if you like, the truth in our machine learning. These are what we're trying to replicate based on the Cygnus data, which would then mean we're able to predict where we don't have observations. And so the covariates that we pulled in, of course, we have a whole load of Cygnus parameters, and that's combined with things that affect soil moisture. So all of these make intuitive sense as to, these are things that you would expect. This is going to have some level of correlation with the soil moisture. So a topographic wetness index, which is based on elevation and flow direction and the upstream drainage area and the slope and so on. Things like the soil characteristics. So there's international soil data available from the Global Hydrological Soil Group, looking at what the percentage of clay and sand and silt is. Saturated conductivity as well, hydraulic conductivity within the soil, global product available for that. That combined with vegetation from MODIS NDVI, Normalized Difference Vegetation Index, and also the GLAD forest height, which is a LiDAR product from the International Space Station. Also combined with temperature, land use, land cover, and other hydrological parameters, including GPM or global precipitation measurements, MODIS evapotranspiration product as well. All of that being combined in one large database. So it's a huge amount of data coming in. So these are pulled into a database and used in our training. And so here's just some examples of what those data look like. And it was through that machine learning training process, it was confirmed that all of those covariates are significant for the prediction of soil moisture. So they were all included. And unsurprisingly, the ones that were most important were things like, has it been raining the last 7 days from the GPM? You'd expect soil moisture to increase after rain, right? The hydraulic saturation, hydraulic conductivity in the soil. How likely is it for the soil to be saturated? That also affects the, whether you've got high soil moisture. Put all those together, and we end up with that pretty plot on the left-hand side between, we got our measured soil moisture and our predicted soil moisture, and a comparison between the two. The one-to-one line, that diagonal line would be a perfect prediction, so it's not perfect. But if you look at the measured versus the different soil moisture products, we're doing pretty good actually. And that narrower error bar on the lower of these plots, that narrower bar is indicating that the range in errors, the variability in error, is narrower than the other products that are available as well. So we've improved the algorithms that are currently existing. So what this does is it gives us confidence that we can transfer this methodology, this approach to predicting soil moisture from Rongowai, which is the key point of all this work.
Is that platform New Zealand or is it for the global?
Cygnus, so it's not New Zealand, except maybe in the far north. So if we compare to one location, one gauge, then we can see that the blue line is the measured and the machine learning prediction line is in red, and we're tracking reasonably well. So just by eye here, it looks, we're quite pleased actually that when the soil is measured as wet, we are predicting it as wet, and when it's measured as dry, we're predicting it as dry. That's good. That's a good starting point. So moving from Cygnus to Rongowai, taking those learnings and that methodologies that we've put together, we now are in the process of transferring that to the Rongowai data. And of course, at the moment, we're still in an engineering phase, and we're now moving towards that science phase. So we're getting towards the point where we're going to be really going at it for processing of the data. And one of the key things here is that because the location of the Fresnel zone from Cygnus is much bigger than from Rongowai, because it's a satellite rather than an aircraft, what that means is that we don't really want to be using relatively coarse data sets like we were doing with the previous training. We're going to be going to more localized data. So a key example here is we'll be using LiDAR across the country rather than SRTM, the Shuttle Radar Topography Mission data. And if we look at the signals we're getting, so one of the key things from the Cygnus, but also from the Rongowai, is that, as Delwyn mentioned, the delayed Doppler map that we have, and a key one is the signal to noise ratio that we get. So how strong is the signal we're getting back? We expect that to vary according to the characteristics of the surface, and according to how moist the soil is, we expect that strength of that signal to vary. And we can see that it does. If we actually look at an example flight here on the left-hand side from late last year, we can see across the country, we are getting a lot of variability within that signal. And if you build that up to all flights for December across the country, we're getting lots and lots of variability. This gives us confidence that we're going to be able to get some really nice numbers out. And again, this is a zoom in for Canterbury region for October through February. Lots and lots of coverage as we build up over time. Lots and lots of variability on the ground as well. So now, next job, of course, is to change that from that signal into an estimate of that soil moisture. We do have data to use and pull in, some existing soil moisture data. So we have a network of gauges. NEWA has a really great network, part of the TriFlow network. And there's also some council gauges. So we'll be using those data to help characterize what the soil moisture is in that location. And there is the soil moisture active passive data available as well. I think this illustrates quite nicely the differences in scale between the data sets. So the SMAP data illustrates how much variability there is across the country. We see the dynamics happening. It's really quite amazing how much dynamics there is. But if we were to zoom into a farm scale, the pixels on that map on the left are really quite coarse. So we don't have the level of detail that we might need to make decisions about irrigating or whatever at that particular location. Whereas on the right-hand side, we have a point scale observation. So we have lots and lots of detail at that one very small location, but there's lots of variability across the land surface. So I think one of the things that excites me about Rongowai is that it fills in that gap between the two. And as we get more and more data over time, it enables us to build up a more and more complete picture about the characteristics on the ground. And because of a sensor being a sensor at one particular location, not having much variability, in an aligned project, NASA Soulscape gauge network, which has several sites in the US, there's now some sites in New Zealand. And one of the things that here that's going to really help us is they're networks of sensors rather than being one sensor at a particular location. So each of these sites has 21 or 13 locations where you're sensing the moisture content and other variables within that. And they're in Northland and in the far north because of that overlap zone between Cygnus and New Zealand and Rongowai. So it enables us to do a cross comparison between the two products. And lastly, as Delwyn mentioned, we've also been observing floods up north. It just happened that the aircraft was flying in Northland over periods of the storms that came through in late January. And so here we have just following that, 1st to 4th of February, I'll show you what those way we've gone about characterizing whether that's a flood or not in a second. But you can see the points in red are indicating where we are predicting there to be flooding in that location. And we have, because getting ground data for these things is quite challenging, we have managed to get Sentinel data. So this is a European Sentinel-1 spacecraft collecting synthetic aperture radar image. And so you can see all the dark areas along the river network are flooded, right? And they overlay really quite nicely with where we are saying in the Rongowai data it's flooded. The time isn't quite exactly overlaid, so we have 1st and 4th for the Rongowai, and then for the Sentinel it's 14th of February. So it's about 10 days or so after, but still you'd expect those areas to either still be flooding, and actually it was a really wet month through February. So we're pretty confident that actually we are seeing something here in the Rongowai data. And what the data looks like when it's a water surface is a really bright return. That's why you can really see flooding really clearly. So these two DDM plots on the right-hand side, one's a flooded surface, is the actual Rongowai data. And on the right-hand side is a dry surface. And you can see that really big peak on the left-hand side. That's because you're getting a really strong return back to the sensor because of that spectral reflection from the water surface. So, you know, it's quite obvious that it is some water there for that particular point. And on the left, on the map on the left here, we put this together across the month of February. And this is showing areas in blue. The points in blue are areas that are observed as flooded during February, but according to the baseline observation on a grid around about 100 meters grid. So each grid cell that we plotted, if it was dry in December, but we're saying it's wet in February, then we're saying that's likely to be flooding. So you can see across the region, lots and lots of flood detections happening. And if you zoom in and see on the grid that's been done at, doing that comparison between December and February, you can see that those grid cells lying along the river. So where we don't have observations, then we're not able to say, but it be intuitively, you probably can, infer that areas at similar elevations along the river are also likely to be flooded. So one of the reasons why this could be really useful is because it enables a really rapid detection of flooding that's occurring, which you can then use to go and acquire additional data. So task a SAR satellite, for example, you've detected flooding, so you can pull a SAR image in for that location. All right, so I'll hand back to Delwyn to tell us where we're going from here. Lots to do.
So yeah, there's lots of cool stuff going on. which hopefully you realize, but the team's growing, especially once we get to the point of releasing the data beyond kind of our immediate collaborative group, then it'll grow even more. And that is the hope. Operations will continue for the lifetime of the aircraft, which is normally 2030. So we're going to have a really rich long-term data set that's, you know, very, I think is going to be quite impactful for New Zealand in lots of regards. The L0, so the basic data that we collect, data offload, unpacking and archiving is automated. The sourcegate monitoring networks have been established, so you can find those. They're up online. There's a website to access. Right now, we're evaluating and validating the L1 data, and we will have a pipeline process for the L1 by the end of the period of our current funding. So our current funding ends in June. There'll be that pipeline process in place by the end of that. And a number of colleagues, particularly in the US, are presently working with some PhD students and researchers working on looking at the polarimetric data and also oceanographic retrieval. So just saw some early stuff over the ocean that we haven't showed anything because it's early days and it's their work, but that's going to be pretty interesting to look at too. Also seeing how close we can do as getting close to the coastlines. I think that's an interesting zone. And there'll be updates on we have a website, and yeah, that's it, I think. Yeah. Thanks.
Questions?
Thank you very much for the fantastic talk. Anybody have some questions?
So in one of these slides, you showed I think combine the SNAP data and the CYGNSS data. So I'm just wondering, how does this data, which essentially is data complement with SNAP data, how is it different from the data that the columns probably get?
So just for people online, Maria, can you take a microphone for the questions in the room? Thanks. So just for the question in the room just now was regarding comparing the map data with the Cygnus and how they are complementary. I'll skip back to a slide on that, which I think is this one, right? So a lot of the soil moisture products that are being produced from Cygnus use SMAP as one of the inputs into their algorithm. We deliberately left it out because we wanted to use it as a comparison. So we're doing a comparison between the predicted soil moisture and that we have and the Cygnus, but we're also doing a comparison with the SMAP. Which one is it? In the blue one, the second one from the top, there's the prediction between our machine learning and the SMAP. So they're quite close, but there's some variability. But the scale of the data is very different. So SMAP is quite great data set, but it's quite coarse. So you're getting a lot of variability within that sort of area that is being covered. Cygnus is much closer. So, and then we're comparing to soil moisture gauge, which is other location. So the scale of the data is very different between those three things. And all of them are providing information about soil moisture at within the locations that they're measuring. Rongowai is going to come smaller still.
We have another question here.
Can you please go to slide 15?
Yeah.
So I think that Delwyn said at the beginning that it's all about the marriage between sensors and platform, which I like very much, but marriages always have a little secret somewhere. So I wonder in L0, the blue stuff, let's call it proprietary. But at the same time, I think that you say that the algorithm is public, it says there. If I'm going to build whatever operation as consequence of this data and I want to design my algorithm, how can I be familiar with the assumptions of L0?
The L0, the L0 is pretty basic stuff. It's like, you know, number of counts, that kind of thing. So there's a counts to watts conversion that turns into an equivalent power received. So it really is, it's like, you know, if you've got a camera and you've designed that camera, how do you turn that into an image, right? So that it's kind of like, yeah, if you really wanted to get into the actual system design as it is, and you wanted to know the gain between this component and that component, most people don't need to or want to know that. And actually, I don't know that. I can't tell you because I didn't design the system. That's the folks at UM. So the L0 really is pretty darn fundamental. And
so it's standard compression rates or images or
no, all of that stuff that you need for the L1 actually has way more than you would want in it too. And I'd be happy to share with you kind of what the contents of those are. But if you go to Cygnus, we've basically mimicked as much as possible what Cygnus has, and then we've added on to it where applicable. For example, we have a polarimetric ratio because we have polarimetry, but we've tried to keep it as common as possible, just because a lot of those science users will be coming from the Cygnus over to what we're doing. So we don't want them to have to redevelop.
And where are you hosting the data?
That is TBD.
Okay.
Yeah. I'm trying to work that out as we speak.
So no one is complaining about data sovereignty issues?
No, but this is a NASA, because we're a NASA collaboration, all the NASA data is open and we're following that. So with the exception of the down and dirty engineering data, which, but all the L1 will be made available at the very least on a NASA DAC, but it should also be on another distribution too, probably. Obviously, we have to have a local capability because someone's got to answer the phone here when we transmit the L0 off. But yeah.
Next question. No, yeah, sorry.
Really interesting stuff, and yeah, I can see thousands of potential uses for that kind of work. One question I got is, you are training your interpretation algorithm based on some stations, land stations that NIWA has put in place, which I doubt they will be randomly distributed and representative of all the terrains that you are sampling. Is there an issue there, or is there a way that you are addressing that the bias that may or may not be there?
That's a good point. Yeah, of course, there will be an issue there in terms of bias and sampling. But I think the main locations we're interested in soil moisture is in agricultural regions in any case, which is where the gauges are. We're less interested, I think, in soil moisture in let's say in mountainous regions or things like that. So for sure, the algorithm wouldn't do as well in those regions. That's, I think, one of the limitations of these sort of approach that we're taking. But it's certainly something that we can test once we've actually done that process. Yeah.
And if I can chime in, not on the machine learning algorithm per se, but presently, you know, one of the areas that GNSS are is kind of the new areas that people are really trying to expand the limits is kind of more in the stress cases and more heterogeneous environments and that kind of thing. So, you know, there'll be a limit as we get into the mountainous areas. You don't know where your specular return is coming from. It could be coming from several places. So there'll be places that it won't work, but then exploring the kind of up to the boundary of where it stops working is part of what we do as researchers, right? So
thanks.
Any other question?
Is there one online?
Thank you so much. It was a wonderful talk. I have it's a two-part question. The first one is, did you get a chance? I mean, how confident are you with the soil moisture that you get from this mission? I mean, did you get a chance? Because I guess NIWA has the VCSN product, which has soil moisture with it, which is a 5 kilometer resolution product, and it uses station data to get soil moisture. Did you get a chance to compare soil moisture from VCSN with soil moisture from this project? And if you are very confident with your soil moisture from this project, do you plan to assimilate that in your NWP model or something? Especially that sort of information would be useful for now casting out extreme events, especially over New Zealand. So take on that.
Thanks for the question. So for international audience, VCSN is a virtual climate station network from NERA. It will be a comparison. And will it do better or not? Well, we've got a measurement in from Rongowai at a particular location, whereas VCSN is an interpolation of measurements. So they're very different. So will it do better than? I would hope so, because we are observing at a particular location. But it's certainly something that would be comparable. And in fact, one of the things that NERA might be interested in, got a couple of NERA people here, would be to use Rongowai to help improve the interpolation algorithms within VCSN. So a simulation approach, yeah.
Could you just go back to slide 24, please?
Renumbering slides would be useful. Can I? Yes, maybe.
Yep. So I just had a question about the kind of S shape in that, or not one-to-one slope on that line. So to me, you're doing not so well at the boundaries of the observation.
That's correct.
Yeah. And that's because you're using a random forest method where the predictions are a weighted mean of the observations, so you can't possibly extrapolate. So my question is, have you thought about using any other machine learning algorithms?
Absolutely, yeah.
Or using there's a method that calculates the degree of extrapolation from a random forest that you can use to say kind of how confident you are and how near the edge of your measured data set you are.
No, it's a great question. Thanks for that. Yeah, of course, there's some bias within the predictions in this, and that bias is also present in the others too. Partly that's as a result of the scale of the observation, as well as the algorithm. So, you're comparing to a point location where actually your observation is not for that point location; it's for a region around that point location. So there's inevitably going to be some variability within that zone. So yeah, we're a little bit too wet where it's very dry, and we're a little bit too dry where it's very wet. Absolutely, using other algorithms is on the table for comparison. I would really like to bring in ones that include spatial variability in them, like a CNN. I think that's probably the direction we'll go. At the scale that we were looking at here, it made sense to go with the random forest as a really kind of an early one to apply and see how well it does. And yeah, it turns out it does pretty well with some limitations.
So particularly in the middle, like it's really bang on the one-to-one, but as you get to the outside, so it depends what you're interested in. If you're interested in soil moisture at the flooding end or the very droughty end, then there's improvements to be had there.
Yeah,
if you're in the middle, what you've got there looks really unbiased. So
yeah. I mean, gauges are great, right? Because they're actually like really accurate for that one really location. The trouble is we can't have gauges at every particular location we're interested in. So we need to have some way of getting observations or predictions where we don't have those gauges. So that we're always going to be dealing with this. And I think this is a good step forward. But there are some issues like that at the extremes that perhaps we could do better for.
If you'd like to use the degree of extrapolation algorithm, I can give it to you.
Oh, cool. That'd be good. Thank you. Catherine.
Yeah, I was really interested to see the flood detection graphs that you put up. And I was wondering if you could see in the future if the granularity would be fine enough in the data and the precision good enough, if you could use this sort of information just to map river width on a day-to-day basis and potentially use that for areas where you don't have any gauging sites, but there is still irrigation happening.
The answer is yes. And one of our colleagues in the US, it's not Clara, there's somebody actually doing that work with Cygnus data and extrapolating that and applying it to this. Yeah, that'd be really fun and cool, and definitely want to do that. The thing that I really, in looking at the data, it's very obvious where to standing water. And it's a very robust binary indicator, water, no water. And what we do need to do, like we've got tons and tons of observations over Lake Taupo, is basically deconvolve the antenna pattern from that to see just how sharp of a detection we can get. And we haven't done that yet, but that's absolutely a great idea, and yes, must be done.
As I've got my hands on it, there's also a national model between width and flow.
Yeah.
So you could convert back from width to flow. If you're interested in that, I can give you that as well.
Awesome.
Yeah.
I think there's two.
Yeah, I really enjoyed the talk. Thanks. I'm wondering if you could talk a little bit about from a technical perspective, what's controlling the resolution at which you feel like you can grid the data? And are there any potential opportunities for improvement there in the future?
There's a ton of opportunities. So we gridded the data because I wanted to compare 2 time periods and see flooded versus not flooded, and that requires kind of putting them on the same, place. A lot of, I was just playing with this literally the last few days and going a little crazy. We only have because of the way that it fills in, and we only have a few months of data, there's kind of an optimal. As time goes on, you'll be able to grid it more finely because we'll have more time record to compare against and for that baseline. So it's kind of going to be a fun project of figuring out the optimal, I think. And then you've got the geophysics of it as well. It's just your when you've got specular scattering, so if we're talking standing water, then it's going to be, we can calculate what the real area is based on the Fresnel zone, the incidence angle, and the geometry of it. So then we can come up with a real number if that's of use. What is the real resolution? And it varies. It varies as opposed to incidence angle. So
it's in the order of tens of meters. So that's
yeah.
Sort of scale.
So for things like braided rivers and Christchurch, where we have lots of coverage, and looking at SWOT, I think these are 2 very compatible data sets.
We're flying over the Waimakuri all the time as well, which is probably quite useful. There's a couple at the back there. So one online. Shall I click? Question online from Charlie. Hi, Charlie. Really exciting stuff for large spatial and temporal sensing of the land surface. I'm curious to know what sort of data streaming application has been utilized to handle the large amount of data being generated, and how do you plan to scale it up for use on multiple aircrafts? Oh, multiple aircrafts. You want to take that one?
So from what I'm used to, this isn't large amounts of data. It kind of is, but it's kind of not. So from the perspective of, we land and we transmit all of our data in the turnaround time that it takes to service the aircraft and turn it around, and they're pretty quick at turning it around. So that was one of the reasons we went for GNSSR, is we could actually, cope with that compared to, getting gigabytes per minute off a synthetic aperture radar, which is more the realm that I'm used to. That said, there is a data processing pipeline, but right now, because we don't have the operational L1 in place, we're still kind of doing some calibration, etc. We have literally, my research scientist is processing the L1s for us to look at on using MATLAB and just by hand. So it really is one of the powers of this is there's beauty in its simplicity, as opposed to what I'm used to doing, where there's beauty in its complexity. So I think scaling up to multiple aircraft would, if we had the sensors, actually wouldn't be that hard from that perspective.
Well, I think
it's still last 1 or 2.
1, 2. Here's the
if there is some sort of vegetation on the top of the soil, does it affect the accuracy?
So questions regarding what signal we're getting back from the soil, what depth, and whether the vegetation will affect the signal. You want to answer as a radar person?
Well, I think one of the questions was the question what Matt is comparing with in terms of the gauge depth. Okay.
At the surface. surface soil moisture. So with the top 5 centimeters.
And so we're an L-band signal being, GNSS. And so what we get is representative of the first couple of centimeters of the soil. So it really is a surface measurement. What was the second part of your question? Undoubtedly there would be, we'd have to look at the various sites, but that's one of the things that we hope to get because we now have polarimetry and we want to start exploiting those signatures. That should hopefully give us some more information about what the surface properties are, including vegetation, because that absolutely will affect your signal.
We have to run out of time, haven't we? But we'll be hanging around for other questions.
Well, thank you so much, Delwyn and Matt, for coming today to give us this fantastic talk. And thank you all for coming. Looking forward to seeing you again in our next session.
About a month.